It's 2-5-15, and we're going to look at the 4D problems. So now you've gotten fairly familiar, and I think most of you really got through those pretty easily. The biggest problem that I am still seeing, yes, the notes just end. The biggest problem that I'm still seeing is people being confused by reading the problem and understanding the situation. And that's something that just doesn't go away. So you just got to really look carefully at each of those problems. In 4C, you learned to sort of, I'll call it play with coefficients of friction. So suddenly you're able to calculate the mass of something because you can figure out its gravitational force, or you can figure out the force that's needed to be applied to it to keep it from moving. You can figure out what its, whether or not it will slide. So you can figure out all those things based on coefficients of friction. Now, you knew there was a next step. Based on coefficients of friction, now you're going to start looking at problems where you're figuring out net force, and from that you're doing some kinematics. So this kind of harkens back to where we went from 4A to 4B, and we went from just figuring out the net force to now, oh, things are moving. What's its acceleration? What's its final velocity? How long does it take? So things like that. Let's start with the sample problem. This is on 146. And, yes, ma'am. And you should probably go back and do some of the ones that weren't assigned, or redo some of the ones that were. And the other thing I can do is I can pull together, if you would like, the 4A, B, C, and D FIPS, and you can kind of take those home and do them as a take-home test, where you have all kinds of problems mixed together. What I will do, what I've usually done in the past, is because the 4C is honestly, it is easier than the other sections in this chapter, I think. I will do a combined 4C, 4D FIP, so it'll be those kinds of problems together. And a lot of the 4D, you're kind of doing a 4C problem to get to the next part, you know what I mean? So, okay. Let's do this. We have a student moving a box of books attached to a rope. We pull on lots of things with rope here, and that rope is at a 30-degree angle above the horizon. And the box of books has a mass of 20, so we'll list everything up here. Mass is 20.0 kilograms. Coefficient of friction is 0.5, and this is kinetic friction, 0.50. And the force being applied, the F applied, is equal to 90 newtons. Okay, so what we want to know is the acceleration of the box. Mu, it's a K. It just is a really bad K. Let me fix it. There. Okay, so that's mu K. What we want to know is actually the acceleration of the box. Well, that's dirty pool, because in order to do that, we have to know what? The net force. So what we're going to end up with is something that we can put in to that. Okay. So the first thing we want to do, whenever we've got something where we have to go to net force, is we need to look at the force diagram. So we've got this applied force on the box. What other forces are there? Gravity, everybody's favorite. F sub G. What other forces are there? Normal force. Wow, you guys are good. You do this like in perfect unison. I love it. Okay, what other forces? Friction. Force of kinetic friction. Okay. So we've got those four. What else do we need to do here?
Find the X and Y of the force applied.
Well, we need to split up gravity, because there's going to be an X and a Y with gravity. So we'll have,
Wait, the force applied or gravity?
oh geez, force applied. Moly moly. Force applied on the X. Thank you. Didn't finish that second cup of coffee yet. It's a thin excuse, but it's the only one I've got. And a force applied on the Y. Okay, so we've split up gravity, and force applied on the X will be force applied times cosine 30. Okay, apparently I just keep saying gravity. It's the force applied, so it's going to be force applied times cosine of 30. And on the y, that will be force applied sine of 30. Just keeping you guys on your toes, that's all. See, it's working. Okay. So let's talk about, we're going to set aside our F equals ma for the moment. Let's just stick it in the corner, we'll come back to it. Let's talk about our sum of forces, x and y axis. So, is this thing rising off the pavement or sinking into the pavement? Nope. Therefore, sum of forces on the y equals what? 0. And, you know, we can look at all the forces on the y. We've got F of g, which is down, plus F sub n, which is up, plus F applied y, which is up. So we know, you know, we don't need to do a whole lot here, but okay, sorry, whenever the alarm goes off on the iPad, it pauses the video, so that's what happened. Okay, we don't really need to do anything with this, but we can look at this and know what the normal force is. Oh, do we maybe? Well, there are two ways to do this, interestingly enough. Two ways to do this. Maybe not. Okay, so let's go ahead and create an expression for normal force. So we're going to have the negative of force of gravity, which is down, minus the force applied on the y, which is up, and that's going to equal the normal force. Now where we're going to have to be careful is in making sure that our signs in the first place are correct, because, you know, we're going to have to pay real careful attention to what the initial signs were based on direction and what they turn out to be. Let me move some stuff around here to make room. Record. Okay, so we've got an expression here, and in order to find the force of kinetic friction, because we don't have that, you know, we've got F of g, we've got F applied on the y, so we can find normal force. In order to find the force of kinetic friction, we're going to have to use mu k equals, okay, what over what? Fk over Fn. Okay, so mu k times Fn, I'm really running out of room here. Mu k times Fn equals your F of k. So you'll be able to plug that back in. Oops. There. Okay. So at this point we have an expression for Fk, which will go in here. We have this, the F applied x we said was F applied cosine 30. So the acceleration, well, mass times acceleration will equal mu k Fn plus that. Great. Now we just have to get that expression for Fn and put that in. So I'm going to move and shrink some stuff. Okay, so we'll resume. So plugging in the expression that we created up here for Fn, let me color code that somehow. We can put this in for Fn. We've already inserted a nested expression for Fk that involved Fn. So now we've got this thing to work with. So let's do a little bit of work with the algebra to make sure that our normal force is correct. Here's the big question. In this case, is normal force going, this is sort of the gut understanding of the problem. Is normal force going to be more or less than the magnitude of gravity here? Less. Because we have a force that's being applied in opposition to gravity. So let's, and this is what your lab, that your box of your favorite things lab, it's basically designed just to get that concept, to look at how normal force changes in situations where forces are applied upward and downward. So, well, it'll be fine. If we look at this, well, I'll tell you what, let's just get through this and then we'll do a whole separate thing to talk about that concept. But that's an important concept. Okay, let's copy this and go to a clean page, shall we? We shall. Okay, so in essence what we're looking at is a situation where the normal force plus that force being applied on the y equal gravity. If they were greater than that, this thing would be rising up into the air. So the normal force itself is going to be less than gravity. Okay, let's get some numbers in here. Let's also solve algebraically. So if we can divide the whole side over here by mass, we've got acceleration. It's not so hideous, right? All right, let's plug in a number. Okay, so we've got our numbers in there, and we're not even going to do the dimensional analysis. We could, but just to check our intuitive thing that normal force is going to be less than the magnitude of gravity, this will end up being a positive number, this f sub g, because it's the negative of a negative number, and we're subtracting a positive number. So the magnitude of normal force is going to be less than the magnitude of gravity, and that's what we want. Okay, so in terms of thinking about this sort of as the whole picture, we know that it's moving in the direction of the applied force. So we've got to make, we can do one of two things. We know that the acceleration should be in the direction of the applied force. We are overcoming friction here. So what we need to do is have it be applied force plus f of k, and then this is a negative number. So we're subtracting that. All right. So this whole thing solves to 75.6, and 90 times cosine 30. Yeah, 77.94, etc. Okay, so the thing to remember is that this is the direction in which the acceleration is going to happen. Make that a positive, subtract your 75.6, divide by 20, and there's your answer. So acceleration is 0.117114317 meters per second squared. Is that what you got? Okay. Okay, so let's look at this conceptually, because this is where these kind of problems become challenging. When we go back, God, that's a mess.
I see where the FK should be negative.
Yeah. When we go back to the sum of forces, copy, paste. Okay. Okay, when we get back to sum of forces on the x, because this is really where we're solving for acceleration, you know, we can write this either way. We can write that it's the f applied on the x plus f of k, or vice versa. It doesn't matter. But what we have to do sort of intuitively, not intuitively, just in terms of applying the picture to the math, we know that the force applied is this direction, and we are told that it is moving. We know that the force applied is greater than the force of kinetic friction. And if we want our acceleration, we know that our acceleration is going to be in this direction. So we want to make this a positive number and this a negative number.
Okay, so
Is there an opposition?
since FK equals UK times FK, would that make both of those things negative?
Just get the magnitude of Fk. Because, well, when you get into, and mu k is never negative. Your coefficients of friction are never negative. What we're looking at is the magnitude of the force of kinetic friction, and knowing that we have assigned that direction to be a negative.
Right, if you put brackets around that whole first part and then put the negative, it's easier.
Put a negative in front of it. Does that make sense?
Yeah.
Okay. We're going to do more of these. Scale of 0 to 5. 0, I don't know what friction is. 5, I'm ready to go all by myself. Okay. Okay. 3s, 4s. Okay. We're going to practice a lot of these. Did I give you the 4D packet yesterday? Okay. Pshaw. 0.12 meters per second in the direction of the applied force. And they say to the right, but nowhere in the problem does it say right or left, so that's just something they assigned. And, you know, we've talked about the fact that some of us sort of intuitively draw our arrows one direction, some draw them the other. So I would just say 0.12 meters per second in the direction of the applied force. Okay, what I'm going to suggest, do problems 1, 3, and 4 in the book. Let me find and hand you the 4D packet. There they are. And we'll do the odds there. But don't panic about those just yet. We're going to work on these tomorrow together. Monday you will do the friction and forces mini lab. So let's talk about what you're going to need real quickly for Monday. Monday, we need shoe boxes. 1 per lab group. If you want to work in groups smaller than your lab group so that everybody gets a real sense of what you're doing, you can. If you want to just buddy up, it's not a real formal lab. It basically looks like a worksheet, but there's a lot of calculation that goes into it because you're calculating normal force and frictional forces repeatedly. So you need a shoe box for every group that we have that's going to work together. And you need a few of your favorite things, and then we will sing relentlessly the song from The Sound of Music. Because I love it. And we will mass your favorite things, and you will put them in the shoebox, and you will attach a string to it, and you will drag it around the halls like your pet rock, with a force meter attached. So you'll know how many newtons of force it takes to overcome static friction, and how many newtons of force it takes to maintain a zero velocity, meaning your applied force is equaling kinetic friction. And you'll do a bunch of calculations from there. It's lots and lots of fun, I promise. It actually is kind of fun. It's goofy. It's weird. And since we traditionally do this lab with Christmas cookies in the boxes, you're welcome to bring in edible things to be your favorite things in the box, and then you can eat them while we do calculations if you would like. And if you don't want edible things, you can just bring in, you know, hairbrushes. One year a group forgot, and so all the girls in the group cleaned out their purses, and that was their box of things. So, you know, doesn't matter what it is. You can use my tape dispenser if you forget your stuff. But for Monday, you will definitely need a shoebox per group and some of your favorite things. So that's it. Work on the book ones. I'll hand you the packet, but we'll work on those together tomorrow.